Today, instead of this big Mark Zuckerberg show, so I hope it's going to be much better. I will think much better. Today I'm going to talk about a randomized method or to do convex optimization. And this will be joint work with Nicolas Leroux, who might join Facebook, Mark Schmidt, who might join Facebook. That's sad. Anyway, so the context is large-scale machine learning. We want to do predictions from large amounts of data. And in this talk, I will mostly focus on supervised learning. And in that setup, there are two or three quantities which are important for the scalability of the problem. The first one is the size of each of the observations. So P, in this talk, and typically, P might be very large. So in the context of computer vision, P will be the number of pixels. And N will be the number of observations, which can also be very large. Okay? And K, which I won't talk about today, but I think it's an important problem, is the number of tasks you might want to solve on your data. For example, for computer vision, this might be the number of objects that you have in the image. You may have one task per object. So the goal here, this talk, is to be able to have algorithms which run in the size, in the time which is linear in the size of the data. So if you make no assumptions, it's O of Pn plus Kn, and the goal is really to achieve this in this talk. So the sad thing is that we're going to go back, most people go back to a 50-year-old or 60-year-old algorithm, Orbit Monroe, and not a lot of progress has been made since that day. It's caricaturing, of course. And today the goal will be to improve on this and to really fight to go beyond this like 1/T convergence rate, which is usual for Orbit Monroe, to get to the geometric convergence rate. So just to set up the stations, I'm going to consider supervised learning with input data xi, yi, and I'm going to consider linear predictions on top of features. So this is just to presenting and motivate the method, but most of the algorithms can be applied to any cost function which is the sum of terms. So here, for machine learning, that sum of terms is typically a sum of errors on individual pair of observations. So the loss, and this talk we only consider smooth losses, like logistic or squares, and some regularizer to prevent overfitting. So what are the main concepts I will need to use in this talk? The first one is the smoothness. Okay, so essentially, I will consider functions for which second derivatives are bounded. So here, this means that the Hessian matrix has all of its eigenvalues which are bounded by L. So on the left, it's not smooth, and on the right, no, on the left this is smooth, and on the right this is not smooth. Okay, so throughout the talk, my function will be smooth. The other concept, which is the other direction for bounding the Hessian, is strong convexity. Okay? Oh, I forgot. In the context of machine learning, having a bounded Hessian essentially means that the data are bounded. This is not a very strong assumption. The other bound on the eigenvalues at the lower bound is called strong convexity, and this is a bit stronger. So essentially, a function will be strongly convex if it is also differentiable or twice differentiable. This corresponds to lower bound of the eigenvalues of the Hessians, and you can also have the same definition if you are not smooth, and namely the value at theta 1 is greater than the tangent at theta 2, which is that guy, and plus some quadratic term that will grow when the difference between theta 1 and theta 2 grows. So on the left, this is convex, but not strongly convex because you have a flat part over there, and this one is strongly convex. So for machine learning, this becomes a very strong assumption. Why? Because in our context, the Hessian, okay, if you take least squares, for example, the Hessian of that cost function is the covariance matrix, or the empirical second order moment, and it will only be invertible if you have more observations than features first. And typically, even if it is, you have enough observations, it's going to have a very low eigenvalues. So you always have to be careful when people talk about strong convexity that the constant might be very small. So since it is typically very small, people add a term, typically a square norm, okay, mu over 2 times theta squared. But you have to keep in mind that the value of mu has to be small. Why? Because if you take a bigger value, you create some bias into your problem, and you solve a different problem. So really, when you think about like learning bounds, which will involve strong convexity, think of mu as being small and going to 0 with n. Okay, typically between 1/√n and 1/n. Okay, so just a review on classical techniques for that setup. So you have gradient descent. which is the most classical technique, and you go down the direction of the gradient. And essentially, the quantity that measures the hardness of the problem is strong convexity. So if your problem is strongly convex, so if you have curvature at every point in every direction, then you get this linear convergence rate. So at every time step, you cut down the error by a fixed amount. Whereas if you just convex, so if you may have like strong correlations among your features, then the convergence rate drops to something which is 1 over t. So this is very much slower. But the key property of gradient descent, which people often overlook, is the fact that you don't need to know in advance if you're going to be in this situation or that situation. The exact same algorithm will be working as well as it can in the two situations. In particular, you don't need to know the strong convexity constant when you start. Okay, so this is really important. I will come back to that later. Then Newton, I won't talk about it because it's not so scalable in our setup because you have to invert a linear system. What is the key insight from Léon Bottou and Olivier Bousquet and others before is the fact that for machine learning, our cost functions are very specific. Okay, there are averages, so you may be able to use this to get faster algorithms. And finally, you may not need like very high precisions. Okay, so if you have an average, it typically fluctuates with a width of 1 over root n. So at the end, optimizing below 1 over root n may be wasteful. So this is why people do stochastic approximation. So what is stochastic approximation? Is those are techniques which are aimed at minimizing a function f, but which you cannot observe. Okay, so in another context of machine learning, f will be the expected loss on unseen data. So f you never have access to, but you have access to unbiased estimate, which I will call f prime n, which is an unbiased estimate of the true gradient f prime of theta n. So this has been studied a lot in signal processing, in setups where you have additive noise, but for machine learning, the natural setup is to consider one loss for each observation. So when you see an observation, it creates a loss function like this. You can compute this gradient, and if with some simple assumptions, the expected value of the gradient on a single observation, it will be the gradient of the expected loss. So this is really the key framework that we're going to use. So the key algorithm from the 50s is the Robbins-Monroe. Okay, so here there's a subtle change. Now the iteration number is n. Why? Because in that setup you see observations only once. So the number of iterations is exactly equal to the number of observations. Okay, so every observation or iteration, you go down the direction of the negative gradient, and you can do averaging. You can do averaging at the end of the algorithm. The key problem is how to choose the step size. Okay, so this remains somewhat of an open issue, and so the best possible rates of performance are known for the problem. Okay, so essentially, like for deterministic optimization, the key quantity of interest that will characterize and measure the hardness of the problem is also strong convexity. And now the rates are 1 over n mu if you are strongly convex, and it goes down to 1 over root n if you're not strongly convex. So here, maybe the most important aspect of the talk, is those rates are on the expected loss. Okay, whereas an optimization rate will be on the training loss. Okay, so here, it's 1 over n mu for the test loss, okay, and it goes down to 1 over root n. So this is a classical setup, okay, and what I'm going to, and this has led to a lot of work, okay, so I hope I've cited everybody in the room. Going to a lot of work, but the goal of today is to look at the particular situation, which is very common in practice, so before doing this, the goal is to go beyond a single path to the data. In stochastic approximation, you see every observation only once, okay, and at the end, what you have is the bound of the test loss. The problem is that I don't know, for most problems, doing more than a pass is better. Okay, so there is somewhat of a mismatch between the classical theory of stochastic approximation and the practice. And so at the end, what you will do in practice, you have a finite data set, okay? You do multiple passes, but the problem is that as soon as you see and use an observation twice, then you start to optimize the training loss, the training error, and not the testing error. And now, so you might say, oh, but if you do 2 passes, that should be enough. Okay, but often it works better with 3 passes. So then you do 3, then, oh, but I do 4, then you do 5, and at the end you end up overfitting. Okay? So the goal of that work that we have done with Mark Schmidt and Nicolas is to consider really what happens if you do multiple passes. Okay, and of course, since you do multiple passes, you start to overfit. So you may need to add a regularizer to avoid overfitting. Although in our experiments, it works very well even if you don't regularize, and regularize by early stopping. So this is not the topic of today, but this works very well in practice. So at the end, what we're going to do will be to minimize an average of functions. Okay, so Fi will typically be the loss of 2 predictors parameterized by theta for the data point indexed by I. Okay, so we have seen like 2 sets of techniques for that problem. Okay, so the first one, so this is an average function, this is our loss, and we have seen a gradient descent. Okay, so gradient descent is nice because it has, if you assume strong convexity, you're going to have like a linear convergence rate. So you're going to converge very fast, but the problem is that to form a gradient, you have to take the gradient of all functions and then average them. At the end, the complexity is linear in n. Okay. This is the bad point. The good point is that you have line search, so things are easy. Okay, so at the end, the good thing is that you have a line search, you have a fast rate, but you're going to have very costly operations, and at the end you make a few steps, but those are costly. So stochastic gradient descent can also be applied to that setup. Okay, so now we have a finite number of functions, and we're going to sample with replacement from that set of functions. So of course, it's efficient almost by design. So at the end, the complexity does not depend on the number of observations. Yeah. So here I went back to t because now the number of observations is fixed and forever fixed, and t is the iteration number. Okay. So this is just be careful with this. So yeah, it's fast iterations which are independent of n, but there the convergence rate drops. Okay. Now you go to 0, but you go to the optimal predictor in your class. The global minimizer of the cost function, you go at speed 1/t, which is much slower. And on top of it, you need to select the step size. Okay, so this is really something which is hard to do in practice. Okay, so now we are close to Christmas, so we should have a wish list for Santa Claus, and the wish list will be to get the best of both worlds. So this is a picture from Mark Schmidt, he's responsible for this. This is comparing like stochastic methods and deterministic methods. So in the x-axis you have time, and in the y-axis you have in log scale the distance to optimum. So the deterministic method will go down as a line because it's a linear convergence rate, so it's a line. But you have steps because even before doing anything, you have to look at the entire data. So it takes a while before even doing one step. Whereas for stochastic, you start to optimize as soon as you see a single observation. Of course, at the end, it's going to flatten a bit because you have this 1/t convergence rate that kicks in. The goal is to start fast and to finish super fast, okay? And hopefully by having this hybrid method. So many people, in fact, they do in front of a large problem like this. They start with a few passes of stochastic gradient descent, and then they switch to let's say LBFGS. What we propose, it's much simpler, just everything is integrated, and people have tried in large companies, and it does do something like this, right? You benefit from the stochasticity at the beginning, and at the end you converge very quickly to very good optimum at the end. So what is the algorithm? This is what we call the stochastic average gradient. So the main idea is that we're going to store the gradients. So at every time step, like in stochastic gradient, we select one function at random, compute the gradient. And then we store the value of that gradient. So this means that at every time step of the algorithm, you have stored values of all gradients. Some are new, and some are old. Okay? So this is essentially what I've been, this is why it is the value of the stored gradient of function I at time t. So if you select that function, you just update the gradient, and if you don't select that function, you keep the old versions. So now, since at every time step we have a stored value, or have an estimate of the gradients, we can take the average, okay, of all of these and make a step toward that direction. Okay, so this is really at the end a very simple algorithm. And simple and not new. Okay, so this was an algorithm, in fact, from Blatt et al. From 5 years ago, where the only difference is that they replace, they consider cycling through the data instead of random selection. So since this is like a workshop on randomized algorithm, this is the key point here. So when we started to work on this with Mark and Nicolas, the goal was to analyze their algorithm, because typically randomizing is easier to analyze than cycling. And we discovered that not only we could analyze the problem, but you could make much bigger steps. In particular, gamma, when you randomize, can be quite big, whereas if you don't randomize, gamma has to be small, otherwise you will diverge. And we have seen that by cycling, it's going to diverge a lot. Then you might think, yeah, we have to store gradients. Okay, so that's true, you have to store gradients, but in the context of like supervised machine learning with linear predictions, then the gradients, okay, are all proportional to the features. So you can only store you can only store a real number. Okay, so the storage cost is only O over n and not O over np. Yep.
So why with replacement? It's not a waste?
Okay, so we have experimented a lot.
Okay.
I use sampling schemes with replacement, without replacements, and then once you get to the end, you restart. We have tried everything. At the end, so if you do with replacement, I think if you randomize the order, if you cycle and randomize order, it works quite similar to this. But you have to cycle, and every time you finish a cycle, you have to reorder randomly. Okay, so let's look at the convergence analysis of the thing. So here, we assume that we have smoothness, okay, typical logistic regression. We're going to assume we have some constant of strong convexity, and of course we will allow mu to be equal to 0. And a very important aspect, we have found a step size which can be computed from data, and for which the behavior is good both in practice and in theory. Okay, so this contrasts a lot with classical stochastic gradient descent, where typically the constant from the bound is not a good constant for the algorithm. Here, it is the case that the constants are matching. That constant is a good constant. Moreover, that constant will not depend on the strong convexity constant. Okay? This means that if the problem happens to be strongly convex, we can leverage it and use it, but we don't need to know it in advance. So in particular, locally, you might be like globally not strongly convex, but locally you might be strongly convex, and typically methods that do not need to know this convexity constant may take advantage of it and get like linear convergence close to the optimum. So what do we get? So this is the result from Nicolas and Mark and me. So here we get an expectation of the difference between the value that I will iterate and the best possible as the global minimizer. So here the expectation is because we randomize the algorithm. Okay, this is the expectation over our own internal randomization, and what we're able to get, we get something which will have a constant term, and for the experts in the stochastic gradient, this is actually the stochastic gradient term, like if you make a pass over the data, and we're able to show this linear convergence rate with a rate that will essentially be this one. So if you make, this is for each iteration. Okay? So if you make n iterations, you have done an effective pass over the data. So you have selected n functions, and after you make n iterations, you multiply this by n. So at the end, the expected cost reduction, after a full pass over the data is the minimum, the exponential of the minimum of 1 over 8 and nu over 16n. So let's take a standard setup for machine learning where mu goes down as 1 over n. This is very classical in many of the theoretical analysis. Then at the end, this becomes a constant. Okay? So at the end, essentially, at every time step, every pass over the data, you cut the error by a fixed amount, and this amount does not depend on the condition number of the problem. So this is really, we didn't believe it at first. The reviewers didn't believe it at ICMM, but this is true. And that we're able to be, essentially we're able to beat lower bounds, but we use the extra information that we have a sum of functions. Okay, so if you want to optimize G, you will never be able to beat this B over L, which is a classical lower bound, but we can because we use the fact that we have an average of functions. Then more recent results, what happens if you're not strongly convex? Okay, this is key to show robustness of the methods. And again, we are able to show something with the same behavior as for strongly convex. We have the classical stochastic gradient bound, and then something that will depend on the number of passes over the data. Okay? And the key here is adaptivity to this potentially hidden strong convexity. So it is really important in practice is that if you have to give mu in advance, okay, typically that mu will be so small that it's not going to work. Why? Because if you have to give mu, this means that you commit to this value of mu, and if the true value of mu happens to be bigger, you can't use it. Okay, it's very important to have this constant step size that does not depend on the condition mu. So the proof sketch, I think that very briefly because I think it's funny, it's a computer-aided proof. Okay, so so the goal in all those methods, what you need to do, is essentially to find a Lyapunov function, that will decay at every iteration. Okay, so typically, here the difficulty is that what is at every iteration we have the stored gradients and what iterates. So we need to find a Lyapunov function on n+1 p-dimensional vectors. So it's a bit hard to do. So what we have done is to simply parameterize this Lyapunov function and realize that this condition ends up in a semi-definite program on the parameters of that function. So you can simply use an SDP to find the good Lyapunov function. Okay, so this is really, and then once you have a good candidate, you have to check that this is true, and we use symbolic computations to do this. So I think it's in fact, for the first version of the work, we did all of this by hand, and it took a while. And okay, so maybe I should mention that the relative work. So we published this like 2 years ago, but 1 year ago, and so there's a lot of other methods that achieve similar things, and with much simpler proofs. Okay? So, for example, the SVCA work of Chalet, Schwartz, and Zeng gets similar rates, but with a much simpler proof, and same thing for Julien Meral, with one difference. All those works, at least this one for sure, you need to know the strong convexity constant. Okay? And if your problem is not strongly convex, okay, then it cannot work. So in practice, in our experiments, this makes a bit of a difference. Okay, so some details. So in fact, since we have at every time step, since we have all gradients which are stored in some sort, we can reuse all the classical tricks that you can put on top of gradient descent to make it more applicable to the problem. So you may want to use like proximal steps or like this. We have defined line search. If data are sparse, you can use it also. Okay, so this is, in fact, there's now a toolbox coded by Mark Schmidt, which is available from our web pages. So some experiments, so those are all experiments, so there are many more in the last version of the work. At the end, we compare, like on a somewhat small scale problem, the different methods. So on the left, this is the training cost. Okay, so all of our bounds are training cost. Okay, so being fast here, we have a theory for it. So we should be fast here. Then the testing cost is just, we hope we're going to be fast on the right. So on the left, we can see, like in green, this is SAG, and SAG is essentially this is a log scale. So you see a line here means a linear convergence rate, and we compare to several alternatives. So Pegasus, the steepest descent in green, Pegasus and the RDA or the stochastic gradient, and LBFGS is essentially in purple like this. So the training cost, we do a bit better than LBFGS, but it's about 2 lines of code. Okay, I was able to code that myself, and I wouldn't be able to code LBFGS, I think. And then on the testing cost, then it turns out that we optimize fast the training cost, but after one pass over the data, we also get a good testing cost. We have no explanation for that for the moment. It just happens that the method works also well on testing cost, and we have tried hard to explain this, but we are unsuccessful. Then we have other things which are Okay, so to conclude, so I presented a method which is adapted to minimizing finite sums, typically like training error plus some marginalizer in machine learning. And the key, really the key thing is that randomization was really important for the problem. If you don't randomize, you don't go faster than the gradient descent. Okay, so in the plots here, like the previous method of Bach et al. Would be like this. Okay? Because if you take a bigger step size, it's going to diverge. This is a really interesting effect of randomization. And those guys also have a similar effect. Then some other work which you have done with Eric Moulin, which I presented at the main conference, is also we have been able also to break lower bounds of complexity, but now on the classical stochastic approximation framework, where you see data only once. And if you want to know more, you can look at our paper. And finally, in terms of extensions, there is things which we really care about. So non-differentiable terms, I think for the moment we have the algorithm. You can simply do a proximal step, it works, but we have no proofs. Kernels, I think like Alex, we love kernels, okay? And that love has been hard for us because nobody wants to do it anymore. And whereas some people need kernels, but it's hard to do like a kernel even with a lot of data. So typically you end up with a square number of a square complexity, which is not really reasonable. And the hope is to be able to use those techniques to get not a linear complexity, because it won't be possible if you want to be non-parametric. So hopefully, with a linear, with a slightly super-linear complexity, and finally, make it parallel. So in fact, the SAG is quite adapted to stochastic gradient, to parallelization. Why? Because you have stored version of all gradients, so it doesn't matter if the new gradient arrives late or not late. So I think people try to use this to do asynchronous parallel things, but for the moment we have nothing really strong on it. Thank you for your attention.